Alright, so we should be live, ready to go. And let's see. Is everything in order? I think so. So hello and welcome. Welcome back. Good evening, afternoon. Set the clock for 3 hours. I have man, I spend so much time browsing the internet, just curious what other people are doing. But we'll come back to this problem. We'll just keep plowing through, keep going. Got about 30 problems left, a little over 30 problems, 31 problems left. See how far we can get this weekend. Spend 3 hours, take a break. Probably spend another 3 hours. Just see how much time we get in. And I don't have much of a plan for what to do. A lot of different ideas of things. But I can at least have this goal in front of me. I can work through this, and then, yeah, there's a bunch of different things I kind of want to look at, things to do. Yeah, evangelize tomorrow, go back on Twitch, read the Bible for a few hours. So this is an interesting problem. We were looking at this the other day. You can use eval read string to actually call a function that's initially a string. And what I want to do is use this as a means of calling itself. I want to provide a function as a string, and then how do we do this? So, given some function, really, some string, right, what we want to do is it's a string of a function. We want to take a function, and then we're going to give it an argument, which is or take a function, and then we have a string of that function. The function returns itself as a string. Can you? Yeah, you can quote string. You can take a function f. No. See, that's the tricky part, right? Because this is. Can you convert a function to a string? You can quote. It's kind of probably why we want to use strings. I'm not sure. So there's the tricky thing here where you can go from a string to a function, but it's kind of tricky to go from a function back to a string. Because this would be kind of easy to do if you can go from the function to the string. But that's actually kind of tricky because I want to do something like this, like take a function, which we're going to turn into a string. So we have this function. It's going to take some s, which is a string, and what it's going to do is evaluate read string of s, and then evaluate that function, right? So we evaluate whatever s is, read this s, evaluate it, and then we want to return s. So we get this function as a string, which is this, right? Would be that string, and we do two things. We return the string, so return itself. But the thing that's tricky about it is that we need to actually yes, this will return itself. But why do we need this at all? The reason you need that is because you need to call this function. Wait a second. Oh, you gotta bind itself to it. Maybe we want to do it this way. A function that includes a certain binding. Actually, performing the binding in the first place seems like it's kind of difficult. I'm not sure. Excuse me, I gotta really ponder this. Really gotta ponder this. This is not such an easy thing to consider. Kind of wonder what this looks like if you partially bind, like watch this. What happens if you do this? So you're gonna take s, this string, right? Which we know is, let's say it is this function, right? And we're going to take s, and we're going to read this string, evaluate, and then so we get a function back, which is this thing, and we partially bind that function, which is this function, to s, right? So now the result of this, calling this with some s, well, the partial binding, yeah, well, this returned value is a partial function, which now you also want something else in here too. You want, you don't want to, yeah, you want to evaluate, and then you also want to, I guess, evaluate with this parameter s, and then also bind to s. And I want to say, I don't know what happens if you do this. Now, I think that the binding is the thing that's really throwing me off, because I think you end up in like an infinite loop, something like that. Like, I don't know what is this, after all. What do you even get if you do this? I'll leave this stuff in there for now. I'm gonna comment, remove those later. But I really don't know what I'm looking at here. We're trying to do. So there's some function, we'll call it f, right, which we can write as, some function. Like what I want is something like this, like there's some function as a string, and we're going to evaluate read string, this function, and that gives us some function that takes, let's say, takes a parameter and then prints what's in there. So it could be as simple as this. You could do something else though, potentially. So some function. Yeah, okay, that at least prints the function. So I guess that's interesting. If we now make this a function in itself, yeah, has some s, and we'll call it, take this as that. And we call this thing s inside. So we take this simple form and replace this part with s. So we're going to read this string, this function in as a string. We're going to evaluate it to get another function. We're going to provide s as an argument to that function after evaluating. No, this should be after we evaluate. Provide s and we call that function, right? And now this function, we can call this with what we're looking at here, and that'll be interesting. Yeah, this is getting to some sort of combinatorial logic. We're starting to approach that, I guess. Okay. No, we want to call this. Oh, wait a second. No, this is the function, right? Now we want to call this function. Am I missing something here? Cool. Okay, that's neat. So this function, this one, if we call this with this string, it'll return that string. Now, if we take this function and make it a string, do we get what we're after? That's the interesting question. Right now we give it the string of itself. Aha. Aha. You get an infinite loop. Nice. Whoops. Stack Overflow. Okay. Interesting. this only works with this function. That's why it doesn't work with itself. Yeah, okay, that's kind of funny. I don't know how I ended up here. How do we end up with this? I got this feeling like it wouldn't be so simple. Had this idea, this notion, it wouldn't be that easy. Yeah, this is some combinatory thing. It's very, very high level, I guess. I don't know. I shouldn't say that. I should say this is interesting. We got to work your brain in a way that's kind of difficult to understand. It's very funny though. So no, the idea that I had was wrong. You can't simply because it matters what the string is that you're evaluating, right? Yeah. Now what if this is the function itself, right? A function that so maybe. Okay, let's go back. Think about this for a second here. A function f that returns itself as a string. Ironically, that's exactly what I'm trying to figure out, and that's also what I wanted before when I said that something that takes a function and returns the string of that function. Basically, you need to just provide the function that you're calling from to that, and then you're done, right? So it's just kind of like a reference back to itself, which actually can work. But the problem is, you don't just need a function that, so a function that returns a string of itself would actually be a function that provides itself to a function which converts a function to a string. So we need a function equivalent to a function that can convert a function to a string. Now we have a function that can convert a string to a function. We've got that right here. We can go the other direction. Can we manipulate this to give us back the string that we provided in the first place? Right? If we take a string that's represented as a function, so it's actually a function represented as a string, can we then spit back that string? Yes we can. What we actually want to do is, this is a very unusual thing, but we'll take a function that takes a string and returns that string, right? This function as a string. Okay. What are we doing here? This is so confusing. I want to say we got to use some kind of fixed point iteration here to call the function that this string evaluates. So when What we ultimately want to do is this, right? You've got some function you read in, you evaluate it with this you evaluate this string to get a function, then you call that function with itself effectively as a string, and this function s is that whole thing. It's the function that does this. And then you provide that whole thing to the function, which then just creates an infinite loop. Ultimately creating an infinite loop. Nice. We may want to use like not the Y combinator, but to use like the Turing combinator. So this gives us infinite loop. But actually, what is interesting is given a certain f, the lambda calculus. All right, so what you could do in theory is you can use Turing's fixed point combinator, right? And what this will achieve for us is every lambda term x, this will reduce to x of. So what we want is you can quote this function, and that'll be a string, right? Quote the function, return as a string. That gives you a string. Fine. What we want to do is take the function x and provide to it itself as a string, and then that should return. No, that doesn't make any sense. I'm super confused now. Once we've gotten the function, whatever that is, we can write it as, I feel like I need to do this more abstractly, like geez, this is crazy. So let's just say like what we want, right? So this function that returns, we'll call it f, function that returns itself when you call it. Okay. A function that returns itself as a string when you call it. All right. How can this be achieved? Well, this function could take another function as a parameter, right? So it takes another function as a parameter, and then calls that function. Oh, excuse me. I want to say something like there's this f which takes a function g, and then it does some things with g, calls g of g, something like that, or just calls g with g. This feels like it's important or useful function here, this thing. That takes a function as a string, reads the string to get the function, and then calls that function. And then calls the function with this string as an argument. Excuse me. There's another function that's kind of useful, or might be useful here. It's this self-replicator, which takes a function x, which you then call x with x as a parameter. And let me go lie down for a few minutes here and ponder this question. The idea is, okay, call this x with an x. That's kind of what the one below it is doing. So it's actually, yeah, it was a self-replicator. It's what it is. It's just in string form. But that doesn't actually do anything for us, because excuse me. Yeah, self-replicator doesn't actually do anything for us. Self-replicator doesn't actually do anything for us because this self-replicator doesn't actually do anything for us because, well, it doesn't do anything inherently. I mean, it just calls itself repeatedly, but basically. If you provide the self-replicator, right? No, I've actually the self-replicator provided to itself is what I just did previously, but with strings involved. That just creates like an infinite loop, which is pretty funny. What you want is more like the Y Combinator, which is a function. You provide the self-replicator to a function, which the result of that is a function, and then you, right, so call that, then you provide the result of that to a self-replicator. Now that's confusing as all heck. But that's what the Y Combinator does. And reduces to the same thing. It reduces to the same thing as f of that thing. The result of a y combinator is like f of f of f of f of f, basically some function being called repeatedly. And it's not particularly interesting if the thing that you provide as a function only has one variable, I guess. You could say, what you maybe could do is have a function that returns the y combinator, or the string form of the y combinator, so something like that. I don't even remember what it was that I was doing, what I was just thinking. Do I want to perform a fixed point iteration that returns the event at the bottom of it, returns the function which is the string form of a fixed point iterator? The combinatory, that's kind of what I'm getting at here. But the problem is, maybe I just need the Turing combinator, right? And then there's two things. There's a lambda value for, I think, for x, and a lambda value for f. And I think one of these functions is going to be as simple as returning whatever is input to the function, right? Just a simple return. don't know. Oh, this is killing me, man. This is killing me. Right, so I don't have the answer offhand. Definitely not. I don't even have any ideas. I think you may be able to use some combinatory logic here, some lambda calculus, but I really have no idea. Wow, wasn't expecting that. Wasn't expecting to get stuck on this one. Amazing. Oh wow, okay. I mean, I guess it is what it is. Okay, we'll ponder it then. So, quine, I think it's called. Quine returns itself. Function that a program that returns itself. About an f of x that prints x. Yeah, and then you just bind that function to itself. Or you call that function with itself. Anyway, sorry, my mind has been wandering quite a bit. So, one thing to consider is one thing to consider is function that takes some string. Right. Okay. So that's part of the problem, I think, or potentially. If you have a function that takes another function and then prints that function, right? Then you could just provide this function with itself, and that would print what you want, assuming you have a way to go from a function to a string. So that's, I think, the crux of the problem, is that we don't have a simple way to go from a function to a string. If the function is, well, you could provide the function as a string, in which case you can go from this, you can just provide strings, and that allows you to easily get the string, and then also allows you to call the function, because you can go from string to a function. So you can maybe use the functions as strings themselves, in which case now we have a function that takes a string and just returns the string, but we want to call this function as well, or rather, well, that, yeah, if it just takes a string, then we can give the function. But now the problem though is that if we want to call it, we need to, oh, that's very interesting. If we want to call the function, by the way, the only thing that is achieved by using what is achieved by using the Y combinator and or the Turing combinator is you have effectively an infinite sequence of iterations where you have f of x give, you know, some you have to assume there's some terminating point to the some kind of recursive base case that you call you provide to f of x, or we'll call it f of alpha, where alpha is some, I guess, vector of parameters, and you call f of alpha, and you assume that's some base case of f, and then you have that returns some, we'll call it alpha prime vector of parameters, and you call f on that alpha prime, and you repeatedly apply f to each returned value starting from the base case for alpha, and the result of all of that gives you your fixed point iteration, which you could, instead of sort of writing a recursive function and calling that recursive function, you could use a Y combinator given a function that is more or less a recursive function. Yeah. Yeah, and your recursive function need only return, simplest thing is to return two values. And I guess one of those values is like a counter, counts down to something. Single values don't really help you much. in terms of what you can actually compute. It's not particularly interesting. Yeah, this fixed point iteration ends up being something like a while loop, where the one piece is sort of the condition that breaks the while loop, and the other piece is the returned data structure of whatever the state of things that you want to manipulate and or you want returned, which is very much like a while loop. One particular part of the state closes the while loop, and the other part of the state changes over time, or changes after each iteration. That's all well and good, but I don't see how a while loop actually helps us with the problem at hand, right? Because yeah, I should actually not focus on combinatory logic here, I think. It's a funny thing about focusing on something that's not useful. If you can prove that it's not useful, that makes it a lot easier to not focus on it. If you can't prove it's not useful, then you get this kind of infinite loop where you're like, is this even, am I going the right direction? I don't know. How much time should I spend on this? But I can say with certainty a for loop here is not really going to solve our problem. No, it's something else that we got to do here. Something else a little more clever. Yeah, I'm going to put the headset down for a few minutes while I think. Right, so after pondering this a bit, I don't think this requires any recursion at all. I think it's just a simple, there's just a few different things we need to combine to get this right. So you need, it's actually going to be kind of a very large string I think we work with, but so we have a function that does this thing, and we have the string form of that function. And what we want to do is when you evaluate the function, you return the string form of it. And yeah, that's what we want. So we have a few pieces. We have the function itself, which actually doesn't take any parameters also. So we need to do some manipulation where the final result, this function when you call it, doesn't take any parameters and returns that string, which is the sort of final result turned into a string. And what I want to do is ultimately, if you have a function that given a string form of a function will return that string, but the function is itself, yeah, see that's the tricky thing, right? Like what we're going to need to do, that's the rub actually, it's the part I'm kind of stuck on, is I'm thinking that like you can use a let command which will bind things, you know, you can sort of bind things and then what you've returned from the let is like the bound version, you know, a call to that bound version of the function. And then you could stamp that whole thing as a string and provide that as a parameter to your binding. No, see that doesn't make sense though, because because that gives you an infinite loop of strings that are increasingly larger. Like it's not actually possible. Something like that. The problem is that if you try to call the thing and it's a string, it doesn't make a lot of, you actually want to wrap the string in a function that has no arguments, which just returns the string. Yeah, I suppose you could do that, I guess. So it would be like some f of x that returns x, and then you bind, I guess, a string s to that f of x. Sure, and it just returns s. And s that you bound would be just this whole thing, this whole function as a string. No, see that's the problem you run into. Like I said, you keep running back to the same thing over and over again, where if you have some string in, I don't know, man, like you kind of just need like something that takes a function and then converts it to a string, right? Whatever the function is. Maybe you need to use the meta tag to build the string. Maybe that's the problem here. You need the yeah, I think that's really what you need. You need a function that takes a function and returns that function as a string. Ultimately, you need that, and then you got to feed itself in that function. If you don't have that function, you can't do this. I think that's ultimately what it comes down to. I don't think there's any way around that. All right, so if you're given some function g and it's supposed to print g as a string, I guess what you'll have to do is Every function has, suppose it's an anonymous function that's labeled with G. So you'll always have in the beginning of, opening parentheses f of n for space, and then that symbol quoted, I guess, concatenated. So G, or string of G, string of the quote of G, right? Concatenate that with, be the body of the function, which how do you get the body of the function as a string? It's not, come on, man. I don't know. I don't know if Clojure has like a way to get the body of a string of a function. Unless you know ahead of time what the body of the function is. That's the problem, though. You don't know ahead of time what the body of the function should be. If you did know it, then you could return it. Also, sort of the problem is like, if you have a function that given a another function, you want to print the body of the function that you were given. As a string. Function that returns itself as a string. How do you convert a function to a string? Is there a way to do that in general? Unless you know what the function is and just return that string. Otherwise, I don't think you can. I don't know, man. That's kind of difficult. You feel like you need to access the metadata in order to do that. Like what the body of the function is as it was defined. Huh. That's really weird. I think you can do that, I guess, with macros in Clojure. I don't know if you can do that in general in all languages. Dude, I'm stuck on this problem. I'm 100% stuck. I also would like to go use the bathroom again. So I'll be back. Dude, what? Dude. 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 Maybe I should stop saying that too. It makes me feel like a Californian. I'm definitely not a Californian. Yeah, I'll be back. I'll be back. Definitely stuck. Definitely stuck. Somewhere here we've got using the bathroom. Alright, so I'll be back. Right, so I knew, yeah, okay, so that actually causes the program to bug. That's pretty interesting. Now it's black. Sweet. How do I fix this? I think I have to restart. Do I have to restart OBS? What the heck? Display capture is done. Oh, now we're back. Sweet. Okay. Yeah, I'll be back. Okay, so I thought about this problem some more, and I'm pondering it more and more. This situation that I find myself in here. I'm thinking maybe this is a little bit of the word. I think the word is ostentatious, like excessive. Like I really don't need to be solving problems like this to like I just want to get more familiar with Clojure. I don't think I really need to be solving problems like this to get more familiar with Clojure. That's kind of ridiculous. This is like way harder than calling it fun. I guess it is fun, but this is like way harder than is necessary. I really don't know. I mean, just flat out, I'm unfamiliar with what it could be. Because if you want to, so the problem you run into is if you want a function that takes another function and returns the body of that other function, it just doesn't exist. Like there's just no way to do that unless you have a way to access the compiler, like the abstract syntax tree of the program that you're running while you're running it, which some languages I think have support for that, built-in support, but typically you don't have the ability to do that without like actually running a compiler on the function, I guess. In other words, running your own machine on the function, so something to that effect. Like you need some pretty heavy machinery in some sense to do this. If you want a function that will return the body of another function, right? Like, give you in string form as example. Because really, ultimately, what we're looking for, like, is we want the other function to be converted to a string. Given some symbolic reference, we can get the string version of that function from the symbolic reference. If that isn't supported out of the box, then you may struggle to. You have to figure out a way to effectively write that, write the function facility to do that. I don't think this is possible if you don't have that function. Like that's a requirement, I think, is that a function that given another function you can retrieve the body of the other function as a string. Some f that takes a g and then gives you the contents of g. And then this problem becomes trivial because then you can just provide the function to itself. Provide that function to itself. Yeah. Or bind this function to itself. In some sense, maybe you don't need heavy machinery at all. Maybe I'm wrong. Maybe this is what the question is asking: is what is that function? Can you just devise a function that, given another function, will return the body of that other function? And I want to say you can't do that. You could argue that it creates a contradiction, perhaps. Well, it's not that it creates a contradiction. It's just if you knew the body of G beforehand, then you wouldn't need this function, which makes a contradiction, creates a contradiction. So this is only useful when you don't know the body of G beforehand, right? Which is the crux of the problem, because if we knew the body of this function already, then we wouldn't need to reference it. Which is kind of ironic. It's like a meta, it's conundrum type of thing. Seems to be a conundrum. If you knew the body of the function beforehand, then you don't need a function to retrieve the body. And specifically in this instance, this is where we apply it, because we don't actually know whatever the function is that we're going to supply. We don't know what the body of that is. Hence the conundrum. I don't know, man. I don't know. This is too much. It's not really getting me more familiar with Clojure at all. It's not like a practical problem in any stretch of imagination. The other problems we did were a little more practical. They're like somewhat not practical because they're, you know, sort of problems that are highly specific. But yeah, you could imagine a situation that could arise where you might want to do something like that. Whereas this is like, you'll never need this. You literally never need something like this. This is just strictly a brain teaser. Strictly an abstract. Strictly really starting to bother me because I can't solve it. I don't want to move on because I wanted to do all the problems in the set, but this is not practical at all. I don't know. Can you get, so can you say like Clojure access to the abstract syntax tree? Let's see, can we do something like this? Reading, evaluation, and macros, allowing AST and Clojure, genetic programming. Stride. Wow. Wow. How to evaluate AST with better performance. Currently we create AST as a tree where leaf nodes are functions of one argument. Full growth. Can we just like retrieve function body? Retrieve function body Clojure. Is that a thing? Yeah, this is okay. This is exactly what I'm looking for. Nice. Okay, so we can use a macro that'll save the function definition in a meta tag. Right, nice. Oh, that's the meta. That's the. Apparently, that's the way to do this. So you can get the source meta. What does source do? Is that the way we get? Can we get the source code that way? Source meta tag. Maybe that's what we need. Maybe this is what I'm missing here. I just forgot. I mean, I did read about this, but I don't use it enough to really remember what the heck is going on. Metadata. So let's get a function and get the metadata, I guess. Like, what does this do? We print this metadata. So maybe that's all we need to do. Really, is just employ some calls to metadata, and we should be able to figure this out. This is probably impossible without that, I think. Nice. Nil. Perfect. That's what I like to see. Alright, I probably just need to read some more then. Metadata of an object if there is no metadata. Turns an object of the same type and value with map as its metadata. Print meta. if there is no metadata. You gotta be kidding me. Maybe you have to make it a variable. I don't know. So if we do define f as just x of xx, and then we take the meta of the var of f and print this. I really don't know. I'm just kind of poking around here. So you'd want to put the body into like a metadata section, I guess, as a string, and I don't know, man. This is like way too hard. This is too much. Way too much. Way more difficult than it needs to be. Maybe put the body into the metadata of the function. And then, I don't know, and then read the metadata to get the body of the function. And that gives you some method to get the body of a function. So the function would really just be calling the meta. But that doesn't work for a general function, right? Like this gets back to the problem of like we need to know what's in this function to begin with. This is awful. This is terrible. This doesn't make any sense. This doesn't make any sense. This doesn't make any sense. I think this is actually maybe one of those things that are more like an edge case, something that's kind of trivial, something that's more of a riddle than actually anything interesting. If we think about it that way, we may be able to solve this. I have to say I'm not having that much fun with this. Really not having that much fun. So if we do this, right? Let's open up the REPL. Just kind of run through some stuff. So quote, okay, interesting. We string of quote, okay. And now if we call, okay, doesn't make sense. Things that are callable. I want to say some macro that you can call that returns its own name. Like, what if you, I don't know, said something like define like func, which returns func, right? And then you call func, then you have a string of this thing, which I guess would be something like this. See, that seems to be the problem. If you make this an anonymous function, it's really awkward. You know, if you print these two things. I get the feeling this is more like a brain teaser and not that interesting. Like, what if you just do this? What does this do? Is that it? Really? Is that... You're kidding. No, but here's the problem, right? Because you need a name, right? See, that's the problem. You need a name. So like, if I use a let command, right? And I was like, okay, like we define this name to be, and then we just call whatever this is here. Oh boy. But that's the problem. Like, we can't contain this entire thing in a string. It's not. You gotta be kidding me, man. This is ridiculous. This is ridiculous. Gotta be kidding me, man. This is so absurd. This is some function func here. Let's try this, right? Let's call f, and that's going to be f of n of f. So doesn't take any arguments. Is going to return some string, maybe s is what we want. And what we're going to do is we're going to bind f with this is I'm going to call f. I'm going to bind f to this partial of f with this whole thing is a string. But the thing is, this is contained in this string. Like, this doesn't make any sense, man. This doesn't make sense. This is itself, this becomes recursive, right? Like, the binding is the problem. This not just recursive, but infinitely recursive. Then what needs to be contained in this string is all this stuff. but then this needs to contain that string, and then the string contains this, and this just creates this infinite loop. Things containing each other. Alright, let's go learn about quines. There's no way I'm going to figure this out in a few minutes. Like, I don't want to spend forever trying to figure this one out. This is kind of ridiculous here. Spend so much time. Quines. Let's find some examples of quines. A quine is a fixed point of an execution environment. Oh, it is a fixed point. When the execution environment is viewed as a function transforming programs into their outputs, quines are possible in any Turing-complete programming language as a direct consequence of Kleen's recursion theorem. For amusement, programmers sometimes attempt to develop the shortest possible quine in any given programming language. The name quine was coined by Douglas Hofstadter in his popular science book Gödel, Escher, Bach, honor of philosopher Willard von Orman Quine, who made an extensive study of indirect self-reference. Object referring to itself indirectly. Wow. And in particular for the following paradox-producing expression known as Quine's paradox. Yields falsehood when preceded by its quotation. Yields falsehood when preceded by its quotation. This is Quine's paradox. Freak. Programmers, man, why did I decide to become a programmer? What is this? Why am I doing this? Why am I doing this? Questioning my life choices here. Who's got time to mess around with this stuff? What the heck? What kind of decision was this? I'm going to become a programmer. No. Don't do that. Go do something productive. Become a farmer. Just plant seeds in the ground, water them, collect the food. That's all you need to do. Get on with your life. What's wrong with you? Sitting around talking about falsehoods preceding their quotations, but that also yield falsehoods. It's ridiculous. It's ridiculous. It basically says this statement yields a falsehood when preceded by its quotation. Yields a falsehood when preceded by its quotation. So if this statement, so it seems to be a paradox, right? So it's basically, if the statement is true, then it yields a falsehood when preceded by its quotation. And the statement is preceded by its quotation. So in order for it to be true, it also must yield a falsehood, meaning it creates a contradiction, which means it can't be true. So if it's true, it's also not true, which is a paradox. If it's not true, though, that means it doesn't necessarily yield a falsehood when preceded by its quotation. You could say it doesn't yield a falsehood. You could say it sometimes yields a falsehood. Maybe. It's not a paradox. But if you're only dealing with statements being explicitly true or false, and not any kind of nuance, sort of sometimes true, sometimes false, more context, let's say, then yeah, it's a paradox. Oh boy. Paradox concerning truth values related to the liar paradox. The problem purports to show that a sentence can be paradoxical even if it is not self-referring and does not use demonstratives or indexicals. It does not explicitly refer to itself. Paradox can be expressed as follows. So basically you're referring to a general contradiction, which is really a reference to the world state, so to speak. Sort of, it's goes even further beyond referencing not just the statement, but actually the universe itself, right? A falsehood of the universe contradiction, which no statement can ever be true and also generate a contradiction at the same time, right? That sort of definition of true yields no contradictions. The sentence implies that it is false, which is paradoxical, for if it is false, what it states is in fact true. Right. Liar paradox. And linguistic resolution, such antinomies. Attach levels to a line of problematic expressions, such as falsehood, and denote entire sentences would stand higher in the hierarchy than their parts. The form clause about falsehood yields falsehood will be grammatically correct, and denoting phrase denotes itself. Wrong. Belows. Sentence might be syntactically ambiguous using multiple quotation marks. Its exact mate marks cannot be determined. Revise traditional quotation into a system. The length of the outer pairs of so-called Q marks. Expressions determine the Q marks appear inside the expression. Not only for ordered quotes within quotes, but also to say strings with an odd number of quotation marks. Just a quine sentence, in fact, uses an indirect type of self-reference. Shows the indirect self-reference is crucial in many of the proofs of Gödel's incompleteness theorems. Interesting. Interesting. The liar's paradox. Well, if it's, I guess they're saying that if it's false, if the statement is, if it's only, it could only be true or only be false. That's what I was saying, is that you have to suppose a universe where it's only either true or false and nothing in between, in which case not being false means it must be true, right? So if you suppose the statement is true, then it yields a contradiction, which means that it can't be true, it's got to be false. But if the statement is false, then yields falsehood when preceded by its quotation doesn't hold, or this yields falsehood means that, so if this is false, that means this doesn't yield falsehood, which it doesn't yield a contradiction. I guess the indirect self-reference is its own statement. This actually is not totally correct either, in some sense, in terms of being self-reference and not self-reference. It's weird, because the quotation of this entire expression is not this, right? This is a quotation of only this. Yields false when preceded by its quotation. So actually this may just be like nonsensical. I don't know. That's the thing I'm getting kind of confused about. I don't know what I'm even talking about anymore. This gives me a headache, this stuff. But apparently this I am supposed to use. I thought I might need to use some what do they call that? Recursive algorithm. This is ridiculous. This is ridiculous. This is irritating. This is irritating. It's not just that I am irritated, it's that it is objectively irritating. Yeah, this isn't yeah. I'm not just like a what do they call that? I don't know how to describe that. Like there's something in one of C.S. Lewis's writings where he's describing that things do have objective value, right? It's not just your subjective view of things. Like, yes, your opinion is just your opinion, but your opinion does have some value because you have an objective experience of the thing, right? And some people's opinions are awful because they themselves have, what do they call that? A certain degree of subjectivism in their beliefs, which is just gross. I guess I don't know what degree it needs to be gross. But I feel like I'm so unfamiliar with this notion of fixed point iteration and self-referencing and all that stuff, just sort of recursioning, that I'm just like yapping psychobabble over here. Like, I'm trying to like grasp this stuff, and it's just like, this just gives me a headache. That gives me a headache, but I'm just stumbling over my own words here. It's just not. This is why it's irritating. I like things to be steady and simple, and not this like falsehoods yielding falsehoods when quoted shenanigans. Whatever this is some kind of quines paradox. It's paradoxical for some reason. And now I'm trying to explain why it's not paradoxical. Well, it's apparently you've got to assume that you're dealing with true, false, and there's no maybe in between. Which, yeah, definitely could lead to some paradoxes in and of itself. But let's see. So, one more time, let me read this. Yields falsehood. So this statement yields falsehood. Well, that's also somewhat self-referential, right? Implied. It means this statement yields falsehood when preceded by its quotation is the quotation of, and then this says this statement yields falsehood when preceded by its quotation. Quoted. And that quote precedes this. Like, this is kind of just gibberish, though, you know? Anyway, like, it's not even English. Like, quote, the statement yields falsehood when preceded by its quotation. This statement yields like, it doesn't really make a lot of sense. I don't know. I'm not gonna just. Come on, man. Indirect self-reference. Object referring to itself indirectly. Define the function f such that f of x equals x of x. Any function passed as an argument to f is invoked with itself as an argument, and thus is in any use of that argument is indirectly referring to itself. Right, so that's the self-replicating function, similar to the scheme expression lambda x of x, which this looks like the y combinator, I think. is expanded to itself by beta reduction, since evaluation loops indefinitely despite the lack of explicitly looping. Constructs equivalent can be formulated in lambda calculus. I don't know if this is actually the lambda Y Combinator. Indirect self-reference is special in that its self-referential quality is not explicit, as it is in the sentence, this sentence is false. This phrase, this sentence, refers directly to the sentence as a whole, and indirectly, self-referential sentence would replace the phrase, this sentence, with an expression that effectively still referred to the sentence, but did not use the pronoun this. An example will help explain this. Define the quine of a phrase to be the quotation of the phrase followed by the phrase itself. The quine of is a sentence fragment would be is a sentence fragment is a sentence fragment, which incidentally is a true statement. Now consider the sentence, when quined makes quite a statement. When quined, quote unquote, when quined makes quite a statement. When quined makes quite a statement. Quotation here plus the phrase when quined indirectly refers to the entire sentence. The importance of this fact is that the remainder of the sentence, the phrase makes quite a statement, can now make a statement about the sentence as a whole. If we had used a pronoun for this, we could have written something like, this sentence makes quite a statement. Right, but it's super confusing because this whole thing is a statement, you know? You're not making a statement about the entire statement, you're making a statement about the quotation of part of the statement. That's kind of what I'm trying to say, is that this is really confusing, this whole thing. Studied in great depth by W.V. Quine, after whom the operation above is named, and occupies a central place in the proof of Gödel's Incompleteness Theorem. You know, I question all this. I gotta be perfectly honest with you. I'm not sure about all this, man. I'm starting to wonder if this is just insanity, the studying he did, and I'm wondering if this Incompleteness Theorem, therefore, is similarly just insane. Just one of the paradoxical statements held by Quine is the following. This quote yields a false statement when preceded by its quotation, yields a false statement when preceded by its quotation. So if it's true, if this statement is true, then yields a false statement when preceded by its quotation. This quote yields a false statement when preceded by its quotation. So if you say this statement yields a false statement when preceded by its quotation, then you're not dealing with something paradoxical, because this whole statement is longer than this quotation. If you're saying this quotation would yield this statement, would yield a false statement when preceded by its quotation, then this statement is an example of that. Because this is preceded by the quotation itself. So this whole statement would yield a false statement, but that would be, if it's true, it yields a false statement. Okay, all right, got it. I'm sorry, I'm struggling to follow all this. Oh, didn't mean to do that. Oh, my freaking brain. That's what happens when you get into that's what happens when you try to learn about functional programming. You just end up down this freaking a fixed point rabbit hole. Just a fixed point rabbit hole, man. It's crazy. It's crazy. These people are nuts. Just kidding. So, okay. So I got that far. That this statement is this statement, and this statement yields a false statement when preceded by its quotation. This whole statement is this thing preceded by this. Okay, that makes sense. So then if this is true, this statement, then this should yield a false statement, right? It should really be a falsehood, not a false statement, right? It should be a contradiction that it yields, because it's not necessarily a comment about this entire statement, because the entire statement is combined, these two. You say this statement, so if you take this statement and say this preceded by its quotation, the resulting statement should be false. Okay, no, I guess that makes sense. Yeah, okay, so yields a false statement when preceded by its quotation, and then you proceed by its quotation. So now it should be a false statement, but it's true statement. If so, this yielded by this preceded by this as a statement, if it's true, implies that it should be false. And then if this is false, it means this doesn't yield a false statement, which means it yields a true statement, creates the paradox. Okay, I get it now. I understand why the paradox is here. Now, the thing is, though, like I said, you have to assume you're in a binary logical field where not false means true. Because if you have a maybe in there, then this being not, if this is not a true statement, that means that this yields a yields not a false statement. If it yields a maybe, then you don't have a paradox, because you could yield a maybe statement. So this is maybe true, and then or not false, which is maybe true. Then it's not paradoxical anymore. So it might be true. This expression, the whole statement may be true. Can't be true because then you're definitely yielding something that's false. But if it's false, then you don't have a contradiction, because it could be true, it could also be not true. Or it can't be false, it could be true or maybe true. Or maybe. Maybe better than maybe is unknown. You could just say unknown. It's true or false. Or even unknowable, something like that. It's kind of like infinite recursion, maybe. Something like that. Who knows? It doesn't halt. Undecidable. Some variation of these things. I don't know. But interesting. Incompleteness. This is crazy, man. Stuff is nuts. Inherent limitations of every formal axiomatic system capable of modeling basic arithmetic. These results, published by Gödel in 1931, are important both in mathematical logic and in the philosophy of mathematics. The theorems are widely but not universally interpreted, showing that Hilbert's program to find a complete and consistent set of axioms in all mathematics is impossible. Sorry, one more time. Two theorems of mathematical logic that demonstrate that the inherent limitations of every formal axiomatic system are capable of modeling a basic arithmetic. Results published are important both in mathematics, logic, and the philosophy of mathematics. The theorems are widely but not universally interpreted as showing that Hilbert's program to find a complete and consistent set of axioms for all mathematics is impossible. Oh, interesting. Any such consistent formal system, there will always be statements about natural numbers that are true but are not provable within the system. The second incompleteness theorem, an extension of the first, shows that the system cannot demonstrate its own consistency. Employing a diagonal argument, completeness theorems were the first of several closely related theorems on the limitations of formal systems that were followed by Tarski's undefinability theorem on the formal undefinability of truth. Church's proof that Hilbert's and Scheidung's problem is unsolvable, and Turing's theorem that there is no algorithm to solve the halting problem. Interesting. They made all this stuff in the 30s, man. Turing wrote the first actual program in way back when. Anyway, that's a whole lot of stuff. I mean, do really need to get into all of that. Theorem prover. Anyway, okay. Interesting. Probably at some point should go over Gödel's theorems again. We're getting closer now because we're reviewing quines. This is crazy, man. This isn't ridiculous. And Scheidung's problem, challenge posed by Hilbert and Ackermann in 1928. Algorithm that takes as input a statement of a first order logic, possibly with a finite number of axioms beyond the usual axioms of first order logic, and answers yes or no according to whether the statement is universally valid in every structure satisfying the axioms. By the completeness theorem of first order logic, a statement is universally valid if and only if it can be deduced from the axioms, so the Scheidung's problem can also be viewed as asking for an algorithm to decide whether a given statement is provable from the axioms using the rules of logic. Interesting. 1936, Alonzo Church and Alan Turing published independent papers showing that a general solution to the Scheidung's problem is impossible, assuming that the intuitive notion of effectively calculable is captured by the functions computable by the Turing machine, or equivalently by those expressible in the lambda calculus. This assumption is known as the Church-Turing thesis. It's happened repeatedly in the past where folks, I guess if you have, it's happened many times in the past where multiple people would come up with the same ideas independently, which seems really weird. But you could argue something like, well, if they both have the same set of information to look at, and it's a relatively small set of information, then it's probably likely that they would come up with the same conclusions independently. I think that's not an unreasonable thing to suggest. Right, if knowledge is generally something like a breadth first search over an infinite space, where it's sort of each new piece of knowledge is like a linear combination of what you already know, some kind of combination, not necessarily a linear combination, but some kind of combination of what you already know into a new thing, a new piece of knowledge. Yeah, that would make sense. It would at least help explain why you see people come up with the equivalent discoveries independently. I would explain that. Moses Schönfinkel. The Russian. Bernays. Hilbert believes that there would be no such thing as an unsolvable problem. Interesting. Before the question could be answered, the notion of algorithm had to be formally defined. This was done by Church in 1936, effectively calculable. Lambda calculus and Alan Turing. Turing machines either recognize that they are equivalent models of computation. Negative answer to the Entscheidungs problem. It's then given by Church, and independently shortly thereafter by Turing. Church proved that there is no computable function which decides for two given lambda calculus function expressions whether they are equivalent or not. Interesting. He relied heavily on earlier work by Klein. Turing reduced the question of the existence of a general method which decides whether any given Turing machine halts or not, the halting problem, to the questions of the existence of an algorithm or general method able to solve the Entscheidungs problem. Oh, that's interesting. You reduced this question to the other. So if you could solve the halting problem, then you could solve the Entscheidungs problem. Algorithm is understood as being equivalent to a Turing machine, and with the answer to the latter question negative in general, the question about the existence of an algorithm for the Entscheidungs problem must be a negative in general. In his paper, 1936 paper, Turing says, corresponding to each computing machine, we construct a formula unit, and we show that if there is a general method for determining whether unit is provable, then there's a general method for determining whether it ever prints 0. Ah, I see. Interesting. The work of both, whether it ever prints a value, same thing as whether or not it ever halts. That's really what they're getting at. The work of both Church and Turing was heavily influenced by Kurt Gödel's earlier work on his Incompleteness theorem, especially by the method of assigning numbers or Gödel numbering to logical formulas in order to reduce logic to arithmetic. The Entscheidungs problem is related to Hilbert's 10th problem, which asks for an algorithm to decide whether Diophantine equations have a solution. The non-existence of such an algorithm established by Yuri Matiasevich in 1970 also implies a negative answer to the Entscheidungs problem. Some first-order theories are algorithmically decidable. For examples for this include Presburg arithmetic, real closed fields, and static type systems of many programming languages. The general first-order theory of the natural numbers expressed in pianos where axioms cannot be decided with an algorithm, however. Practical decision problems. Having practical decision procedures for classes of logical formulas is of considerable interest for program verification and circuit verification. Pure Boolean logical formulas are usually decided using SAT solving techniques based on the DPLL algorithm. Conjunctive formulas over linear, real, or rational arithmetic can be decided using the simplex algorithm. Formulas in linear integer arithmetic, Presburg arithmetic, can be decided using Cooper's algorithm or William Pugh's omega test. Formulas with negations, conjunctions, and disjunctions. Disjunctions combine the difficulties of satisfiability testing with that of decision of conjunctions. They are generally decided nowadays using SMT solving techniques, which combine SAT solving with decision procedures for conjunctions and propagation techniques. Real polynomial arithmetic, also known as the theory of real closed fields, is decidable. This is the Tarski-Seidenberg theorem, which has been implemented in computers by using the cylindrical algebraic decomposition. Wow, that's a whole lot of maths and philosophy that I am not familiar with. Holy guacamole. CAD. Double exponential, nice. What? Real algebraic geometry. I don't even know what I'm looking at here. This is way unfamiliar to me. Extremely unfamiliar. Holy smokes. Oh my goodness. Let's go back to the paradoxes here. Liar's paradox. Antinomy of the liar. What's an antinomy mean? Contradiction between two beliefs or conclusions that are in themselves reasonable. Okay, antinomial. Alright. Statement of a liar that he or she is lying. For instance, declaring that I am lying. If the liar is indeed lying, then the liar is telling the truth, which means the liar just lied. In this sentence, it is a lie. The paradox is strengthened in order to make it amenable to more rigorous logical analysis. It is still generally called the liar paradox, although abstraction is made precisely from the liar making the statement. Trying to assign to the statement the strengthened liar a classical binary truth value leads to a contradiction. This sentence is false is true, then the sentence is false, but the sentence states that it is false, and it is false, that it must be true, and so on. Right? Just back and forth, true and false at the same time. Not logically equivalent. All cretins are liars. Can be resolved as false, given that he knows of at least one does not lie. It's precisely in order to avoid uncertainties deriving from the human factor and from fuzzy concepts. Modern logicians propose to strengthen liars, such as the sentence is false. Yeah, that makes sense. Okay, I could follow this. The other stuff I'm not really able to follow. Spectivism. Magnum opus. Relativistic, non-committal, or perspectivistic. Everything I am saying is false, hidden parameter which can change on problematic situations to a stubborn paradox. Oh, that's pretty funny. Paradoxes consume themselves. Keep apart the warring sides of the contradiction by the simple expedient of temporal contextualization. What is true with respect to one point in time need not be so in another. Yeah, context. Austinian argument is not really that things change, but that rationality is essentially temporal. In that we need time in order to reconcile and manage what would otherwise be mutually destructive states. Huh, well, that's kind of neat. Factor time, which allows us to reconcile the separated parts of the world that play a crucial role in the solution of barwise and etchemendy. The capacity of time to prevent a direct confrontation of the two parts of the world is here external to the liar. In the light of Petrarch's analysis, however, the extension in time which separates two perspectives on the world or two parts of the world, the part before and part after the function accomplishes its task and inherent in any function. Function to signify which underlies each statement, including the liar. The unsolvable paradox, a situation in which we have either contradiction or infinite regress in the case of the liar, and other paradoxes such as the unsignifiability paradox. When abstraction is made from this function, an extension in time by accepting the simultaneous opposite function, undoing the previous one. Yeah, I don't really know. I guess, sure. Why not? I don't know, man. I can't help but feel like I'm wasting my time reading all this stuff. I can't help but feel like I'm wasting so much time. Okay. Are we wasting our time? Okay. Right. So we got the liar's paradox, quines paradox, logical antinomies. Got it. Clean's recursion theorem. Fundamental results. Application of computable functions to their own descriptions. The theorems were first proved by Clean in 1938. Metamathematics. Excuse me. Kind of feel like the person that just learned what the word meta means, you know, but meanwhile people have been pondering meta things for hundreds of years, if not thousands of years, centuries. Yet the word meta has got this like, oh, what does meta mean? The meta. A related theorem which constructs fixed points of a computable function is known as Rogers' theorem. That is due to Hartley Rogers Jr. in 1967. Recursion theorems can be applied to construct fixed points of certain operations on computable functions to generate quines, and to construct functions defined by recursive definitions. Yeah, I mean, great. You know, all I needed to do was go study this book from 1952, and it would have been no problem to generate this quine. It's a good thing we're spending so much time on this. Good thing I was trying to figure that out just laying in bed. I think if I really wanted to solve, you know, I was interested in Project Euler problems for a while, and it occurred to me that really what I need to do is not sit and try to quote unquote try to solve the problems. What I would need to do is actually go read a bunch of stuff in mathematics, and then hope and pray that whatever thing that I'm looking at in Project Euler shows up in some of the things that I studied, which is kind of ridiculous. Like, it just struck me that like the algorithm to solve all of those problems is actually a lot easier than I thought, because a colleague of mine, or a viewer had mentioned, like, yeah, I know someone at Facebook who solved all of those problems, basically, and I was like, how is that possible? That's amazing. And the truth is that no, they didn't solve all of those problems at first glance, like like on their own volition, their own ability, their own capabilities. They solved them by reading tons and tons of books on mathematics and then just applying each of those concepts to those problems, which is a very different thing than like coming up with the solution on your own. Like, I'm not about to figure out the solution to this problem on my own. I'm about to go learn about quines and the work that other people did on quines and then apply that. It's very different things. These are some very different things that we're describing here. Yeah. I don't know what to make of all of that. Kind of want to go back to solving those Project Euler problems, though. I feel like I wasted a lot of time on that, but at the same time, it's like, I actually know how to do it now. Now I know what to do. I just feel like it's a few years late. I mean, I think I was doing that. How many years ago I started doing that? 5 years ago or something? 3 years ago? 4 years ago? Many years ago now. That I was solving those problems. And yeah, it's weird, man. You could go back to trying to solve those problems. There's sort of no point in that, though. Because I'm not sure, like, yeah, to what end, I guess is the question I would ask. It's like, yeah, it's interesting, but like, to what end is definitely the question to ask yourself. Which is a question I think I haven't really spent a lot of time asking myself lately. To what end do you do such things? Do ye such things? To what end do ye such things? Well, you could argue, well, to be godlike, but I haven't even finished reading the Bible yet, you know, so how godlike can I be? So maybe I should go read the Bible, finish that first, then go read, so I guess I'll go ahead and just make my streams reading the Bible a lot longer. Read the Bible, right, then learn Arabic, read the Quran, then learn Hebrew and read the Talmud. Then we'll go back and start reading math textbooks. Then we can go ahead and start, and then we can go solve all those project Euler problems. And then I don't know what to do after that. I guess go to heaven. Go to heaven after all that. Anyway, that's what happens when you come across some extremely abstract and difficult questions. You question your life choices. You sincerely question your life choices. Alright, so we should be running up on a few hours now. I mean, I know I took a break to use the 20 minutes for now. It will be 3 hours. I mean, I know I went to use the bathroom, but does that really count as taking a break? I guess. I don't know. Let's continue though. So you can construct fixed points of certain operations on computable functions to generate quines, and to construct functions via recursive definitions. All right, let's read on here. Statement of the theorem refers to an admissible numbering, whatever the symbol is, kind of Greek symbols. Hold on, let's go find out what I want to name that thing while we're talking about it. I've noticed in my life I often don't have enough symbols to work with. Don't have enough symbols. We're looking for... What is this symbol, after all? Var phi. Phi. Okay, so that's phi. Alright, got it. Admissible numbering phi of the partial recursive functions. What does that mean? Mu recursive. I think I've gone over this many times and I still don't understand it. Class of partial functions, what does that mean? Of natural numbers to natural numbers that are quote-unquote computable in an intuitive sense. In computability theory, it is shown that the mu recursive functions are precisely the functions that can be computed by Turing machines. Okay, this is one of the theorems that supports the Church-Turing thesis. The mu recursive functions are closely related to primitive recursive functions, and their inductive definition below builds upon that of the primitive recursive functions. However, not every mu recursive function is a primitive recursive function. The most famous example is the Ackermann function. So they're related to the primitive recursive functions, but not necessarily. There is an example of a primitive recursive function that's not mu recursive, which is the Ackermann function. Okay. Other equivalent classes of functions are the lambda recursive functions and the functions that can be computed by Markov algorithms, which is not the same thing as Turing machines. I guess the Turing machine. I don't really understand, but okay. The subset of all total recursive functions with values in 0, 1 is known in computational complexity theory as the complexity class R. Total recursive functions. I don't know what that means. So partial recursive or general recursive, mu recursive partial functions that take finite tuples of natural numbers and return a single natural number. They are the smallest class of partial functions that includes the initial functions and is closed under composition, primitive recursion, and the mu operator. The smallest class of functions, including the initial functions. Enclosed under composition and primitive recursion without minimization is the class of primitive recursive functions. While all primitive recursive functions are total, this is not true of partial. You know, I feel like I need to stop reading Wikipedia because the explanations just don't help me that much. Like I just don't get it. You know, they explain things, but it just goes over my head. I have to read it so many times to understand. I think the problem is a lack of context. Like I don't have enough context to really understand these things. I think I would need to go find like books, other authors to describe what these things are, what they're talking about. It's kind of like hopeless. There's just not enough context to really process all of it. Some stuff you can get, but a lot of it just goes right over my head. Not really familiar enough. Anyway, so okay, so there's these general recursive functions. I at least can get this part. You know, it's a finite tuple, a partial function that takes a finite tuple of natural numbers and returns a single natural number. Okay, whatever that means, that gives you your mu recursive function, sure. So now you've got a partial function, x to y is a function for some subset of x, domain of x. Okay, so partial function is not the whole. Okay, that's probably what a total function means then. It's just the whole. It's defined for all of x. Okay, got it. So you could say Kleen's recursion theorem, fundamental results of the application of computable functions to their own descriptions. Theorems were proved by Kleen in 1938 and Poirier in 52. Okay, got it. So statement of the theorem refers to an admissible numbering phi of the partial recursive functions, such that the function corresponding to index e is phi of e. In programming terms, e represents a program and phi e represents the function computed by this program. Okay, so it actually generates a function. Oh boy. I got 13 minutes to figure out this quine question here. If f and g are partial functions on the natural numbers, the notation f g indicates that for each n, either f of n and g of n are both defined and are equal, or else f and g of n are both undefined. So this is sort of like equivalent f and g. It's a notion of equivalence. Congruence, let's say congruence instead of equivalence. So it's sort of a notion of congruence. Rogers fixed point theorem. Given a function f, a fixed point f of f is an index e such that phi of e is congruent to phi of this fixed point of e, f of e. Rogers describes the following result as a simpler version of Kleen's second recursion theorem. If f is a total computable function, it has a fixed point. Okay. Proof of the fixed point theorem. The proof uses a particular total computable function h, defined as follows. Given a natural number x, the function h outputs the index of the partial computable function that performs the following computation. Given an input y, first attempt to compute phi of x. If that computation returns an output e, then compute phi of ey, returns value if any. Blah, 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 blah. I don't even want to read the rest of this, man. I'm bored already. reflective programming, self-reference in programs. First recursion theorem. Oh man. Alright, so apparently you can do something with quines recursion theorem, but I don't really care to fully understand what this means. Description, there's Rogers fixed point theorem and quines second recursion theorem, which has some meaning and apparently has application of quines. So maybe I do need to go read this if I really want to know, which I don't really want to read these things. Just don't care that much, man. Takes no input and produces a copy of its own source code as its only output. The standard terms for these programs in the computability theory and computer science literature are self-replicating programs, self-reproducing programs, or self-copying programs. Quine is a fixed point of an execution environment when the execution environment is viewed as a function transforming programs into their outputs. Quines are possible in any Turing-complete programming language as a direct consequence of quines recursion theorem. For amusement, programmers sometimes attempt to develop the shortest possible quine in any given programming language. The name quine was coined by Douglas Hofstadter, popular science book. Gödel Escherbach in honor of philosopher Willem von Orman Quine, who made an extensive study of indirect self-reference and in particular, right. So, okay, history, idea of self-reproducing automata came from the dawn of computing. If not before, John van Neumann theorized about them in the 40s. Paul Bradley, and Jean Milo's article, Computer Recreation, Self-Reproducing Automata, discussed them in 1972. Bradley first became interested in self-reproducing programs after seeing the first known such program written in Atlas autocode at Edinburgh in the 1960s by the University of Edinburgh lecturer and researcher Hamish Dewar. The download source requirement of the Affero General Public License is based on the idea of a quine. Interesting. AGPL. Constructive quines. In general, the method used to create a quine in any programming language is to have within the program two pieces: A, code used to do the actual printing, and B, data that represents the textual form of the code. The code functions by using the data to print the code, which makes this sense since the data represents the textual form of the code. But it also uses the data, processed in a simple way, to print the textual representation of the data itself. Following Java code demonstrates the basic structure of a quine. You what? You know, it's funny, one of my coworkers brought up quines to me, and I just completely did not understand what he was talking about. Like, it just went way over my head. I did not realize how difficult it would be to actually produce a quine. I had no idea. I was like, oh, that's kind of cool, like, yeah, but it just didn't. At first, I was like, yeah, of course, but then I thought about it some more. I was like, no. I mean, now I've been asked to write a quine. I'm like, All right, public static void main string quotation mark character array of source code. So you've got this initial part, right? That makes sense. Quotation mark character array of source code. Okay, this makes sense, right? This data piece is string, and then this is where it gets interesting. What do you put in here? What goes here? Array of source code. Comma. Right, so these commas just give you right different lines. Yeah, this is an array, right. So now you have this array of source code. What do you have now? A new space, closing parentheses, print opening code, print string array, print this code. Okay, that's all contained here. And then this is the rest of the code. So it begins here, and then you have this part next. Okay. This part comes next. And there's this extra piece in between. Which I guess is I don't know why. I guess they just decided to put this extra string here. And then this is the rest of the program. Basic structure. Source code contains a string array of itself, which is output twice, once inside quotation marks. Oh. This code was adapted from original post from c2.com, where the author posted it as a minimalist version of a quine without Java comments. So, oh, interesting. So it prints the initial portion, and then it'll print this opening code, this L of I here, prints 6 times this L, prints this 6 times, and then it prints this string array. I don't know what this is. Oh, quotation mark characters 34. Array of source code. Q L6 L of I Q I of length L of length. So each of these pieces you append quotation marks. L of 6 is zero, 1, 2, 3, 4, 5, 6. So you print this. I is less than 6. I'm sorry. So you print the beginning part. Okay, print the opening code. Right? Print the string array, which is this part. For each L of I, each of these values, this thing. L6 gives you this. Okay, I think I understand. So it gives you this tab character plus these quotations plus L of I, right, and a comma. So you print you print all of these. So first you print the opening, then you print this entire thing, and then you say from 7 to the end, you just print this part, without the quotation. So it looks like what you end up doing is you print the beginning part, right, which is encoded here. So you print this portion. Then you print everything inside here, which is what we have, right? Print everything inside with quotation marks and all that good stuff. And then you print the last portion, which is this piece. You print that here. So you end up printing twice. You print this piece in the middle with the opening and ending code, and this piece here. And so you have to refer back to the body of the function. I said that previously. I said that when I was thinking about this. I was trying to figure this out. I said you need a function that can print the body of the function, that can return a string of the body of the function. You can't do that in general. I think I was correct in my. I was thinking that you could do this if you knew beforehand the body of the function, but that would defeat the purpose of the problem, because then you would already know it. I was wrong, actually. They're just looking for any example that you could think of where you already have the body. And in order to construct this body, all you need is something that refers back to some, I guess it could just be some variable inside of the program. And in this instance, you effectively just break up the program into 3 pieces: the beginning, the end, and the middle part. And all you need to do is print. You need print statements that refer back to these pieces, and will print twice the program, or quote unquote prints the program twice. It'll basically print the beginning as needed. Then it'll print the entire copy, right? The self-referencing part, the part that contains the body, and then it'll print the end. So you sort of end up with two pieces of the program. The program itself is actually two. It sort of looks like two. It looks like it's self-copied, duplicated. And the code that actually prints things just needs to refer to this array. So it's actually really easy to do in some sense, but it's not easy to do in general. You could not take any arbitrary function and make it so the contradiction that I ran into is that any algorithm being a quine is actually impossible. You cannot always retrieve you need to know beforehand. Not that you need to know beforehand, but no, you couldn't know before. You don't necessarily know beforehand. No. See, here's the thing that's also tricky about it. You don't know beforehand what it is that you're going to be printing. You know that you want to print some bodies of statements, some arbitrary body of statements, but you actually cannot simply print any arbitrary amount of statements. There's a certain set of statements that fit the quine structure that you can modify into a quine. That's really confusing and nuanced answer, but yeah, that's what it is. Not confusing, but that's the truth, is that there are only a subset of programs that can be quines in the first place and can be quine-like, and so there's only so many things you can even extend into quines. Sort of like the quine, it's like the set of functions that are in a quine closure, and this is sort of a general form for quines, where you could take any function you want, but you've got to dump it into the beginning or the end, and your beginning and end will have to contain these pieces. Actually, you end up with kind of a problem, because if you try to put statements in the middle of here, like in the ending, if you try to put stuff in the ending part, it gets really confusing. I don't know if you can. See, that's what I was saying. You could clearly put things in the beginning. I think that's obvious, right? Because you just have this extra piece here. And I suppose you could put things in the end as well, arbitrarily. But you do need to have this piece in between that prints out the sort of the copy of the code, which is this is kind of the copy without the middle piece. The middle piece is actually just a concatenation of the top piece and the bottom piece, which is weird to think about, but that's effectively what you do. So if you had the body of a function, if you had a function, you had its body, you knew of the body of a function, you could create a quine through this approach. Which, by the way, I have no idea what this looks like in Clojure, so it makes the challenge that much more difficult if you try to ponder what you might do in Clojure. I feel like I'm so limited, so unfamiliar with the language. It's my other excuse for not having figured this out. Yeah, when my friend showed me this, I thought this was super simple. But it's not simple at all. This is like something that really could take a lot of time to figure out. Amazing. Amazing. Wow. So you more or less need a string array of itself, which you print twice. Once inside of quotation marks. The code was adapted from an original from c2.com. Eval quines. Some programming languages have the ability to evaluate a string as a program. Quines can take advantage of this feature. For example, this Ruby quine. Eval, print eval s equals ps. So this so this will actually print itself. Cheating quine, self-evaluation. In many functional languages, including Scheme and other Lisp, and interactive languages such as APL. Numbers are self-evaluating in TI Basic. If the last line of a program is a value returning, the returned value is displayed on the screen. Therefore, in such languages, a program containing a single-digit results in a 1-byte quine. Since such code does not construct itself, this is often considered cheating. In some languages, particularly scripting languages, but also C, an empty source file is a fixed point of the language, being a valid program that produces no output. Such an empty program, submitted as the world's smallest self-reproducing program, once won the worst abuse of the rules prize in the International Obfuscated C Code Contest. The program was not actually compiled, but used CP to copy the file into another file, which could execute to print nothing. Could be executed to print nothing. That's pretty funny. Other questionable techniques include making use of compiler messages, for example, this GW basic environment. Entering syntax error will cause the interpreter to respond with syntax error. Come on, man. This is what I was looking for. I was like, there's got to be a way to do this. Source code inspection. Right, I was going to do this one too. This is quines per definition cannot receive any form of input, including reading a file, which means quine is considered to be quote-unquote cheating if it looks like its own source code. The following shell script is not a quine. Invalid quine reading the executed file from the disk is cheating. That's pretty funny. Yeah. Ouroboros programs. Quine concept can be extended to multiple levels of recursion. Originating Ouroboros programs or quine relays should not be confused with multi-quines. Ouroboros programs and multi-quines. Nice. Nice. We're going deep here. Outputs the source for a C++ program that outputs the original Java code. Excuse me? The Java program outputs the source for a C++ program that outputs the original Java code. Oh, this makes it Ouroboros. It prints the C++ code, which then the C++ code prints the Java code. That's a lot of fun. So you can, okay. Wow, that's amazing. And I guess you need to comment out the C++ code and comment out the Java code depending on. Well, no. This creates the Java program, and then the Java program. Then this Java code creates a C++ program, and the C++ program creates a Java program. So again, I was talking to one of my friends about programs that basically construct themselves, right? It constructs another program, and that program then constructs another program, and you can sort of, you know, keep regenerating programs. I might start getting into sort of pseudo or Ouroboros programming, what they call it, genetic programming, where my code is going to be generating more code, which then goes back and changes itself, and I don't know, man. It's going to get pretty wild. It's about to get pretty wild if I get into all that. But this is pretty cool. I'm grateful to see this. Yeah, I would not have thought of this. I didn't really understand what they mean by Ouroboros, but with a concrete example, now I can get a grasp. Get something to chew on here. But it follows a similar quine kind of thing. It's just a quine within a quine. Really, that's what it comes down to. It's really funny though. That's really cool. This is something else, man. Something else. And you've got such programs that are produced with various cycle lengths: Haskell, Python, Ruby, Python, Bash, Perl, C, C++, Ruby, Python, PHP, Perl, Ruby, Scala, Scheme, Scilab, Shell, Slang, Smalltalk, Squirrel, Standard ML, 128, formerly 50 programming languages. Rex. So someone just went nuts. Someone just took it to an absolute extreme that should never have been approached. 128 of these quines. This super quine, this Ouroboros program. Web application to C. Web application source code consists of HTML, JavaScript, and CSS. Holy smokes, multi-quines. It's not the same thing as Ouroboros programs. Unlambda. Instead of our different programs, our different languages, that's condition we could take them all equal to a single quine, each of which is able to print any of the R programs, including itself, according to the command line argument it is passed. Note that cheating is not allowed. The command line arguments must not be too long. Passing the full text of a program is considered cheating. So it's a quine in a certain language, and then you can give it a command line argument, and it'll process that argument to produce a quine of the other languages. And if it's two languages, it's a biquine. This is ridiculous, man. This is ridiculous. So that's a multi-quine, which is not the same thing as an Ouroboros program, and nor is it the same thing as just a regular quine. Regular quine. Radiation hardened quine. Oh my goodness, you gotta be kidding me. What? Is a quine that can have any single character removed and still produce the original program with no missing character. So radiation hardened can have any single character removed and still produce the original program with no missing character. Of necessity, such quines are much more convoluted than ordinary quines, as is seen by the following example in Ruby. Dude, this is ridiculous. This is absolutely ridiculous. What am I looking at here? This is nuts. How do you even do that? What? You can remove any single character. All right. I guess. Wow. I don't know, man. That's wild. That is wild. I guess it's radiation hardened. That's amazing. This makes me think of like DNA, genetic code, that like you can destroy parts of your body, lose parts of your DNA, and your DNA can be radiated, right? Like from the sun or whatever, your code, and your body can still figure out a way to re-replicate itself. Is your body just a ridiculously complicated quine? Maybe. I wonder. That'd be pretty wild. Quines applied to genetics. Radiation hardened quines. Holy smokes, man. I don't know, man. I don't know. That's difficult. That is difficult. how do you even test that it works? You know, you got to go through, you know, a test case where you try every possible character, remove one to verify. That's pretty wild, man. Radiation hardened quines. That's like something out of like a sci-fi movie. All right. So I think I understand what we can do. You have to basically write the Clojure equivalent of this program, and then we've got ourselves the quine that we're looking for. Harder than you think. No kidding. No kidding. No kidding. Read this if you get stuck. It's worth the effort to solve it independently if you can. Yeah, I don't know. Oh, I ended up getting, yeah, I got stuck. It is a fixed point, but it's not it's a little more special than that. You can't just use a combinator to put this together. I mean, I guess you could put maybe a kind of form of a combinator can be used to convert any function to a quine, like a quine computable function, computing a quine from a function. I don't think so though, actually. It seems kind of obvious now that I'm thinking about it, but I don't know. Like, I couldn't wrap my head around it. Because I guess what you could say is, you know what's really hard? You know why I was really struggling with this? This maintains state. I think you could argue that there's state involved here, and that makes this kind of difficult to do in Clojure, or less obvious to do in Clojure, right? Because once you remove mutability from things, it's like kind of harder. I don't know. I don't want to say that, but it's sort of. Yeah, I mean, you basically need once you have a string array of stuff, then it's a lot easier to manipulate. Yeah, I guess that makes sense. Anyway, yeah, I don't know, man. I don't know. Yeah, that's what you need. You basically just need the body of the function as an array, and then you can manipulate from there. That makes things a lot easier to understand. But without that crucial piece of information, I'm just kind of like, yeah. All right. Let me end here. End at least this clip, this stream. Stop there. Tortured myself over quines. I really didn't want to waste too much time on that. That seems so like, it seems kind of obvious now, but yeah, no, it wasn't good. I don't think I was gonna figure that out on my own. That was too. I was also looking for like a much simpler answer, but yeah, I guess you come to that conclusion. Like I was looking for, I guess, a more general solution, something like that. But like I said, you need to actually know what the program body is going to look, function body will look like. Has a beginning, a middle, and an end. And it's really just a beginning and an end, and the middle is a concatenation of the beginning and end in string form in an array. And so you can manipulate your program. The ending part is just printing out what you find in the middle. It just basically prints two copies of the program. Or rather, yeah, that's basically it. Prints the middle, the beginning, the middle, and the end. That's what the ending does. Yeah, okay, fair enough. Make quines that way. Quine generation. Anyway, thank you all for watching. Talk to you soon. I'll probably be back in maybe half an hour to an hour. I don't know how much time I want to spend or wait before I come back. Just take a break. See how long it takes. Last time I said I'd be back in an hour. I wasn't back for like 2-3 hours, whatever it was. So I'm not gonna make a liar of myself here. Just admit that I did wrong last time, and let's see how long I come back for. I don't know. I just want to take a break, and just kind of relax and ponder what we've uncovered here. Just ponder what has transpired. 3 hours thinking about pondering quines. Radiation hardened quines. It's doing nothing but shake. I'm just shaking my head after that. Alright, let's stop here. Stop here.